Okay, so this is chapter 2, and we're gonna get into language and systems of measurement. Okay, so here we're getting into the measurement system. This is trying to teach you how to measure something. Okay, I'm gonna start with very basic diagrams. So here we're studying a square. So you have your geometry of a square, and each side is 20 units. Okay, this can be any units. So here we have 20 your dimension here, another one side is another 20, 20, and then 20 over here. So review your middle school geometry for different shapes for two-dimensional objects or parts. So here in this case, we're gonna name A, B, C, and then D. Okay, so here in our measurement system, we call the part object. Okay, same thing. Object is the part and part is the object. So we have object A, B, C, and D, or part A, B, C, and D. And they have their own geometry. Okay, we know this one is square and this is rectangular. This is an irregular rectangular. And then this one is another irregular square shapes. Okay, these are all shapes. So now our concentration is we want to measure them. And the question is, what is the size of A, B, C, or D? Okay, what is the size? So in order for you to be able to answer what is the size, you have to measure it. So you're going to measure from here to here, and I got a 20. From here to here, and you got a 20. This and that is parallel to each other. So therefore, the distance is the same. Okay, all the length is the same. This and that, again, they're 90 degrees to each other. So therefore, parallel to each other. Okay, perfectly parallel to each other. Therefore, the size of this side of part A is the same as that. So what about the area? Because we have to answer the question, what is the size of this two-dimensional part? And we always answer by using a dimension called area. Okay, and the area is your length time width in symbol. So we use L for length and W for width. When you multiply them, you're going to get area. And here is your area. So everything is a line here, shaded lines right there. Okay. So the area is the size of this part A. The size of this part B is the area B. Okay. The size of this part C is area C. And then the size of this part D is area D. Perfect parts. Perfect square, perfect rectangle. Here, imperfect parts. Just look at this. See, this line right there is not parallel to that line. So therefore, when you draw a line right here, make a perfect part. This is not a good drawing. So I'm gonna do this and I'm gonna draw it again. Okay, so what's we want to do? I'm trying to make it as straight as possible. So anyway, you got the idea. Anyways, imagine this little red line is perfectly parallel to that line. Okay, so here you can see the extra part right there. See that extra part right here, the triangle. So anyways, if you have an irregular, okay, rectangle, you have to come up with approximate area, okay, for the part that you're measuring, because we have to answer what is the size of that and what is the size of D. But we do have the perfect size right there for 2020, and here we go, 2020. But this one is, see that like how it is not a perfect square? So the lack of this area, because you have a little curve, okay, corner right there. So you're literally losing this, okay, losing that. I'm going to draw exaggerated part right there. So you're losing the little corner right there, right here, okay. So you gotta come up with the idea of this area of D is definitely less than area of A. Okay, it is less minute, okay, area, little corner right there. So therefore you can say the area of D is actually less than area of A. And we know the exact area of A right there. See? So that's a 20 times 20 is going to give you 0, 0, 2 times 2 is 4, so 400 units square. Okay? Right there. So therefore, we know that the area of D, or the size of D, is less than, a little bit less than the size of A. Okay? And this is how you measure parts and then come up with approximation for the imperfect part, okay, by using the standard or perfect part right here. All right, now let's think about part C. So the part C, what is the size of C? The same thing, okay. You have to come here, and we know 30 times 20, okay? So if you calculate 30 times 20, you're gonna get 600, right? So here, you'll be getting, I'm gonna write that down for you right here, 600. Since unit is unknown here, we'll just use the unit. And then this is time 2 times right there, so therefore it's square, okay? 30 unit time 20 unit is 600 unit square. That's the area of B. Definitely C, okay, when you look at it, 30, 30 the same, 20, 20 the same. So I'm gonna draw this line, and I'm gonna draw this line here. So you can see this little part right there, okay, about that much. So if you draw it. So that's the area, okay, less than B. So therefore, the size of C is less than the size of B. So therefore, the size of B, okay, C is going to be less than 600 units square. All right, so I'm going to give the size of A is 400. We don't have a unit, so therefore, we can just write it down, unit, the whole square. Here's a blank unit, so you can put any kind of unit that you want to make. This guy is 600, so that guy, you see, that's only 19, that's 20, sorry, this is 20, and this is 20, so therefore, we, in this, okay, irregular rectangle C, doesn't have this part, okay, which is this part, little part right there. So therefore, the size of C is less than 600 unit square. So all you have to do is the size of C is less than 600 unit. I'm not going to write it anymore, unit square. Okay. The same thing with D. When you look at it, 2020, I have 2020, but I have an edge, a curved edge right there. So therefore, you're losing this tiny little bitty bit of area right there. So therefore, the size of D, okay, is less than 400 unit square. Okay. And here I'm just trying to tell you about R, and we use that in some of the graph and some of the irregular, okay, diagrams. So we call that the square root of R squared. It's just trying to show you because this R square root of R squared is nothing but you're looking at like this, because we usually go by R square anyway. When you square root, okay, the R square, you get R anyway, okay? It's the same thing. So the meaning is how close the data are to fitted regression line. We will come to this later in the chapter. So if you have a very low R squared, okay, which is this one actually, not the square root of R squared, but R squared. R squared is pretty low, okay, that means that the model does not fit the data well, right? Meaning like this guy. So this is your model. That's kind of like my standard, okay? So this one compared to this one. And here we're not dealing with R squared in this course, but then I just want you to review, all right, R squared and then the square root of R squared if you're taking physics or mathematics, all right? classes, then you can be able to understand what they are. So every time we're dealing with the imperfect parts or irregular parts, then we deal with this model if it's going to fit the data or not. Okay, but right now you can just go lightly for this too for now, and just concentrate in the size and how we deal with the irregular, right? Irregular part. What do? We compare them with the perfect parts. Okay, their dimension here in this case is the length, width, and then the area. And then we estimate whether the part that we're trying to measure with the irregular shapes is bigger or smaller than the standard or the part that we're measuring, okay, the ID parts. So that's how we come up with a lot of the estimation. Okay. All right, so I'm going to erase this board. So here we go. The lecture video used the PowerPoint, but then we're using the PowerPoint as a board, okay? And try to think like you're just looking at the board in the classroom. It's the same thing. Definitely not the presentation, okay, regular presentation that you have to do on site. All right, so next. Okay, so here you just get yourself familiar with the terms. Okay, so here if you buy the textbook, you're going to get to that. If you don't buy, use the handout, and it's right in there. So here we're giving you two tables right there for the linear measurement in decimal inch. Decimal inch is nothing but, okay, they come with the 0 point and then 0.5 and then 6, let's say, of an inch. Okay, we're too familiar to like 1 inch, 2 inch, okay, 12 inch, kind of like that. But now we're getting into very small, okay, small length or width or whatever we're measuring. So the linear systems are right there. So if you go by the decimal, meaning you might have like 2 decimal or 1 decimal or 3 decimals, all right? So these are just the showing you the very small measurements, and we call that decimal inch, okay, because it is way less than an inch. We also have inch pound, okay, decimal, because they are less than 1 pound, so therefore you have inch pound combined with inch and then pound together, and the matrix system. So inch pound is another word for the British system, okay, and then the matrix system is our SI, okay. If you have already taken your physics 1 and 2, you know SI system. We call the matrix system in America, especially in the industry. They don't use the SI system. Okay, they only use this one. I think it's because of a lot of the businesses in ancient time are based on the British colony and things like that. So still they're using the inch pound system. Go with the pound and then go with the inch instead of meter. Okay, and the kilograms. So those are up to you. So some people love to do the SI and some people love to do the inch pound. Okay. Anyway, so you can go ahead and write it this way and then say it that way. Okay. Definitely not going to ask you anything in detail. So if you read it and can be able to answer the quiz question, maybe a couple of the questions are based on this table, you should be fine. Taking the quiz shouldn't be that hard, because we're not asking you anything to remember anything, okay? But all you need to do is read the assignment and then look at the questions and then find the answer from your textbook or your handout. You don't really need to buy the textbook, okay? Everything is in your handout and the PowerPoint, and you can listen to the lecture right here, okay? I will definitely emphasize the key points that you definitely need to know in this course. And the quiz is not MCQ, so you have to download the file, answer, and then upload your answer file back into the quiz, so there shouldn't be any kind of issue doing that. All right, let's go to the next one here. So here, you definitely need to know the size and the term. Understanding that, okay, people don't like the word understanding, but you have to know this, okay, somehow. So if you don't like the word, don't use it, but definitely need to know size and term, or get an idea of what is size and term. be able to measure the size and be able to say the term, okay? So whichever way that you want to say is fine. So here is a length. So here you can see the Empire State right there, building. And here's a little penny right there. So this is a length of the penny, okay? So this length of this penny compared to this Empire State, this is like a 1 millionth of an inch, if this is an inch, okay? So you can imagine how a million of an inch, how small that is, okay? So you can imagine a penny. That is a million of an inch if it is compared to the 4 Empire State Buildings distance, okay, from the top all the way to the bottom. The same thing right here. So 1 million of an inch. This is 1 million of an inch. So you have a 60 right there. 1, 2, 3, 4, 5, 6. Okay. So that little distance is 1 million of an inch. If we imagine, okay, from here all the way to here is an inch. Okay. So from here to here is an inch. So 1 million of an inch is this. So Baltimore all the way to New York. Imagine the same thing again. This is a kilometer, okay? And if I imagine this is an inch, okay? Wait, we're gonna go to millimeter, sorry. So if I imagine this is 1 millimeter, and this little one is going to be 1 million of 1 millimeter, okay? And we call that 1 micron, right? So I want you to go over this again, read it carefully, and feel, okay, how small the million is. In numbers, we write it this way. So you have 6 zeros, okay, behind the decimal. In millimeter, we use a micron, okay. For inch, we go million of an inch. This is your inch pound British system, and this one is your metric or SI system. How far? Okay, how far again we measure by using the principal measurement, and that's your length. We already know that you have already done a lot of math, okay? So you're the university student right now, so I don't have to go over this again, okay? Length, or we use L. Sometimes we use, this one is your meter in metric, okay? This is your symbol. This is the symbol of the unit, meter in SI. Your length, we go by L or little l. That's a big L. And then you have some sort of numbers. I'm going to write it down for you. Let's say I have a 25, okay, meter. So that is a representation of the length measurement, okay, and we use this way. So you have a number, okay, representing your distance, and then we have a unit. Okay, here I'm using SI. You can also use mile, okay, the same thing. You can use inch or feet, okay. You can say like 25 feet, so that would be, you know, inch, pound, or British. Okay, I'll go pound right there. This is going to be your mass, okay? We're not writing mass right here. So if I go time, you can also write right there, second, or minute, or hour, okay? Many different kinds of quantity. So anyway, right now, we are looking at how far. So we're dealing with the linear measurement, okay? So the length. Secondary measurement, even though how far, we use something called angle, right? So that's represented by degree, this little symbol right there. And we measure curvature, and that is also how far, okay? Don't get into circle measurement. Circle is also how far, even though they're going in a circle. So anyway, K, and then per meter. Okay, per meter is in mathematical way, it's going to look like this, 1 by meter. Okay, 1 by meter is equal to meter to the power minus 1, and we call that per meter. Okay, so here you have hidden 1. So if you move this up, okay, go back to your algebra, then you have a negative power. Okay, review your mathematics. Degree, the same thing. If you want to measure from here to here, it's wiggly. Anyway, this is your degree. Okay, let's say that's 20 degree. So the distance from here to here is a curvature, and we measure the distance from here to here by degree. Okay, so therefore it is under how far? Dimension is nothing but an expression of a measurement value. We have a measurement value, and then you're going to express that measurement value, and we call that dimension, two dimension. So you're using length, okay, for your length, and then your width, and then you multiply that, and we call these things two dimensions. Three dimensions, you're going to have a height factor in it. Okay, so getting into 3D. Alright, so use them to describe features or size. So their surface finish, flatness, and angular relationships. Okay. Curvature, your review from your mathematics or physics. It measure how fast your direction changes. Okay. Because it can be like that, and then your direction changes. So these are all curvature. Okay? These are your curve. Every time the direction changes, we call that a curvature, and it measures how fast the direction changes. Anyway, don't need to get into too much details. If you know, like, we use length as a principal measurement. Secondary is angle for measuring the distances. I don't know how far from one place to another, one point to another. Okay, we use this two measurement systems. All right, next one. Okay, measurements. So you have some sort of measurements right here, and this is your value, and it is in decimal. I have 4 decimals after the decimal point. So I have 1, 2, 3, 4. I have 3.2301. That's my measurement. Okay, and here is a decimal point, right? So never leave. Okay, now there's somebody talking outside. Anyway, so never leave a blank in front of your decimal. If you don't have any kind of number, let's say I have 3, 2, okay, here is my decimal point. If you don't have any number, do not leave blank. You're going to put in 0 right there, okay? So that's the correct way of writing the 0.32. The measurement, we use some digit of significant figures on the report. So here I have 4 significant figures, okay? So 1, 2, 3, 4. This is 0. 0 means absence of, okay? Absence of. 0, the meaning of 0 is absence of. So I don't have any value at this position. So I have a first position, second, third, and a fourth. They're all significant, right? Because they have value right there. So 1, 2. And this guy doesn't have value, absence of value right there. But then I have a presence of value behind this guy, okay? So therefore I have to count this. So in order for me to count this, you have to count this position even if you don't have any kind of value in it, okay? So therefore 1, 2, 3, and then 4 significant figures because they are significant, okay? You can't get rid of it. So therefore 4 significance right here for this example number. So significant figures begin with the first digit to the left of the decimal point. Okay, that is small 0, and the end with the last digit to the right. Okay, that is correct. So if you read it, you wouldn't understand it. So we have to show you, you're going to do the supplement review, which is going to be a separate document that I will be uploading in Canvas and under chapter 2. Okay, you're going to study the significant figures or review from your high school. Okay, so you will find that page on Canvas. Okay, so if we go by the significant figures rule, you're going to get 1, 2, 3, 4, and 5. You look at the decimal point, you look at the left. So I'm going to draw that for you here to the left. Okay, that's not 0, so therefore we start counting. So that's 1. Continue to count 2, 3, 4, and then 5. Yeah, and this is all the way to the end. Okay. But in the lab, like I said, we only concentrate this one. We don't care about this. So we usually say this for significant figures, and you will encounter that when you get into the lab, okay, laboratory data or something like that. We ignored the very first one. So that is, I believe, is the greatest discrepancy that you will be seeing in the lab and outside in your high school or somewhere, okay? And you will get very much confused. Oh, am I doing the right thing? So anyway, so the original rule, okay, that we use for calculation is that. But when you come into the lab, we usually ignore that thing, and we only say this like for sig figs, because you have to concentrate, you know, on decimal, okay, unit more than the whole number right there. Okay? But when you're doing SAT or ACT, okay, now you're like getting into university, and you're gonna face that confusion of the significant figures. So the point is we are ignoring everything before the decimal points, and we only pay attention to all the units after the UK decimal points. Okay, and both are right. So anyway, you can go with the first rule right there, because this textbook is pretty much, I think, based on high school. So therefore, just go with the regular rules, the original one. And here, okay, in the quiz, you can give me 4 sig figs, okay, as a university lab, that's fine. Or you can also give me 5 with the high school, okay, rules. Both of them are correct, okay? You don't have to debate about it. Both of them are correct. Regular mathematical way, and the other one is commonly used in the real world way. Yeah. So anyways, review your supplemental review. Okay, if you're okay, you understand the significant figures, and there are only a couple of questions, right, in the quiz. So if you get it, I think you should be fine. All right, next one. So linear measurements, a unit of length, and a multiplier. Okay, so here, when you look at it, this is a bulky explanation of this, just a value with a unit. So here you have a unit right there, 8 hours. Okay, the value is 8, and then your unit, we're using a time here in this case, measurement, 8 hours, and this is your unit. Okay, and I'm gonna write it here. HR is abbreviation, HOUR, hour. Okay, S. Some people use a little bit of S right there, another variation that you can see. But then the standard is you don't need to do this plural thing right there. You just go HR dot. Okay, but then we have a lot of misconception outside and on the online. So you will see like people writing like that. There's an incredible amount of confusion going on outside because they're not conforming the standard way of writing. They're writing like whatever. Okay, so if you go into the science online, they're gonna correct you by cutting this thing off. Yeah, let's just go with HR. So when you go HRS, that's fine. So whatever you want to do, but whatever that's a unit, this HR is a time, hours. Yeah, we have value 8, usually a number, and then hours. Yeah. Now let's go back. Multiplier is your value 8. Your unit is hour, HR. Okay, HR dot is abbreviation of HOUR. That's it. And we do not care about singular or plural at all. It's not English language here. Now let's get back to our textbook. So this will get a cutoff from your textbook, and here is your multiplier 6 and 30 for the odd numbers. And then you have your unit of length, your inches, your seconds, your miles. All right. So 6, 30, and 4. Going back to middle school. All right, numbers, these are cardinal numbers. Just a review. Multiplier smaller than 1, okay, are expressed by a fraction like this. So if you have like 0, 0.25, okay, 0.25. Yeah, that's a 25% of 1. Yeah, so therefore that's 1 by 4. Okay, a quarter. So this is called fraction, and that is called decimal. Yeah, fractions or decimal multipliers for those who are smaller than 1. Yeah, less than 1. What is this? Let me see. Okay, anyway, so I'm just gonna write it back here. Less than 1. Yeah, less than 1. Okay, here we have 6 inches. That's your unit, and that's your multiplier, cardinal. 1 by 2 is your fractional. Another unit, foot. 0.5 is a decimal. Another unit, foot. Multiplier, unit. Multiplier, unit. Multiplier, unit. The multiplier can be cardinal, fractional, or decimal. Okay, now we're going to continue to study multipliers. So multiplier is very, very large. Look at the 3,000, 1,000, very large multiplier. Okay, they're more conveniently expressed by using exponent. Okay, exponents are nothing but it looks like that. You have a base 10 most of the time. We have many different bases, by the way, but most of the time, for at this stage, you're going to be using 10. Okay, and then 10 to the power 9. Okay, why? Because we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, zeros. Thus, each 0 is 10. So 9 0 with 3. Okay, so 3 times 10 to the power 9. So we use exponent to express very large multiplier. Okay, here we go. This is very small multiplier. Okay, so we have, again, look at the number. So we go 3, going backwards. So getting into the decimal. So therefore I have 1 0. We're going to call our base is 10. There's only 1 0 going to this direction, meaning a smaller, getting into decimal. So therefore minus 1. Okay, going to this direction, bigger. Okay, dimensionally bigger and bigger. You count the 0, the number of the 0 equal to the power number. Yeah, the number of the 0 going that way, so meaning getting smaller. You have your value times, count the 0 after the decimal. There's only 1 right there. 10 to the power. Negative mean going that direction. It's a vector, kind of like a vector. Okay, here there's a positive right there, meaning like going to this direction, increasing. Okay, all right, so we're done with the multiplier and the unit. So that's for your linear measurement. You have to be very clear about all of that. Okay, if you're confused at the foundation, you will be always confused. Okay, so clear that before you continue. All right, next one. This is just showing you an example of little objects right there, so you can be able to understand the size of that. So very, very large, going all the way to 29. So when you look at this, okay, base 10, 29, you know that there are 29 zeros. Okay, there is no value right there. So if you see this, we have a hidden 1 right there. Okay, times 1. So therefore you have 1, and then you have that many 0 after 1. Okay, that big. Very small, the same thing. Minus. It's just a direction showing you going to the smaller side, going that way to the decimal side. Okay, how many you're going? You're going to start with 0, and then you're going to start your decimal. That many 0. Okay, so you're going to go 12 0, ding ding ding, all the way down 12, and then you have a hidden 1 right there times 1. So it's going to end with 1. Yeah, you have 12 0 after the decimal point. Ended with 1 because there's no value right there. This is hidden. Okay, so now I get into this table. So when you go into this table, you're gonna see a grandiose term right there. Don't freak out. All you have to do is just understand the 1,000 of an inch. So 1,000 inch, we call it, common word is mil, right? M-I-L. This is happening only in the United States. Okay, other countries don't use that at all. They're going with SI. So 1,000 inch is a mil. Okay, 1 million This was an inch. We already know that, yeah? So here, the same thing. You can see all the exponents right there. Every time you see the exponent, you gotta get this, okay? So if you see that, that's what you have, okay? 29, 0, blah, 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 all the way 29, 0 after 1 comma. Okay, that big. So if you look at the exponent, don't feel afraid of it, because they're just language, a term, okay, mathematical term, telling you, trying to give you a very compact or precise way of writing very, very huge and very, very small number, because it's a waste of time writing all that zero, yeah? We're going to just code it. I have 12 zeros, and I am going down all the way to the decimal, okay? Smaller decimal. I have 29 0. My number is pretty big. I'm going this direction, okay, to the bigger direction. And you should be able to, just by looking at it, you should be able to know the size of it, okay? How big that is, or how small that is. So practice that, okay? Practice that, looking at it. Know that this is a number of 0. Know that this is a number of 0 after decimal, okay? That is before the decimal, yeah? And each one of them is beginning with 1 or ending with 1, yeah? If you don't have a multiplier right there. If you have a value, then sometimes you have 3 or 4 or 5, whatever number that is, you just cap it with that and end it with that, yeah? The same thing. So if I ask you, what is this size of that? You should be able to say that's 10 to the power 5, yeah? That is starting with 1, comma, 5, 0. So if I ask you, where is my negative? Oh, here, 10 to the power minus 7. You should be able to write it very quickly, 0 point. Okay, decimal is your point. So you're going to start 0 point. And then you're going to have 7, 0. Okay, that's the number of 0. Go all the way to 7, dot, dot, dot. And then end it with 1, because there's no other number value given to you. Yeah? And practice that. So if you have like a multiple choice or short question or whatever, you shouldn't be spending less than 2 seconds for this. Yeah, you don't have to spend so much time on very easy one. And the key point is here. You know that this is the number of 0. The positive and negative are direction. Okay, direction. Where is it going? Positive going that way, going up. Negative going that way, going down. Okay. So what is our starting point? Your starting point is your decimal point, okay? This one before the decimal, okay? This one after the decimal. Your direction minus, direction plus. Minus and plus in mathematics, okay, are also linked to the natural sciences. Chemistry, biology, physics, mathematics, the same thing, okay? Because mathematics is just a language to describe all the complicated thing in a very simple way. So just by looking at the signs and the number, you should be able to understand what they mean physically in your head, okay? So if you see that, you know that's a direction. We always, a lot of the things in the world are based on 2 directions, okay? Either we have everything that you can see in the real world, okay, with what you can perceive with your physical system, and everything that you cannot perceive is in we represent that with lack of, which is your minus in presentation. Okay, plus is everything that is present, lack of, and this is present. Okay, 0 is empty. Okay, there's no value in it. 0 has no value. Okay, nothing. We also call the 0 the same thing, both of them in it. Okay, plus and minus together. Very difficult to understand, but then when plus and minus together, we got something called null, all right? And you can break the null into making it something that is there and something that isn't there, okay? Lack of, presence of, lack of. When they combine, you got the null. So anyway, you kind of get it. You're in the technology anyway, so don't forget any of that basic principles. So anyway, we're done with this thing. I believe you get it. So we're gonna go next one. Alright, so dimension, features, and measurements. These are just the terms, okay, that we use in the measurement system. So you have to know these terms. I already mentioned what dimension is already to you. So let's go back to our common term. Dimension is an expression of a measurement value. Just an expression, okay. Designer is nothing but who is making the part, okay, concept for a perfect part. Just pretty big word. We're just talking about a part, okay, a perfect part. A perfect part, and we call that dimension. Let's say this is a 40 units from here all the way to here. So a perfect part is going to give you the exact 40 units from here all the way to here, okay? Another common word, toolmakers, machining resulted in the feature of the part. Feature, another term, it's just a perfect part, okay? Perfect part that is showing the exact value of what has been measured, okay? And next one is measurements, inspectors, measurement. Verify the toolmaker's work, okay, to the designer's concept. So we're just comparing this with that. And here is your measurement. We're measuring this part by using this instrument, and we get that measurement. And the measurement in number is 40.03. You compare your measurement with a perfect, okay? A perfect part right there, which is your dimension from here to here, and that should be 40. But then your measurement with this instrument, we have an error of 0.03. Okay, I think you kind of get it. Ideal, real life, using an instrument. Every time you use an instrument and somebody using that instrument, there is an error. What is the amount of that error? Is this much, 0.03. Okay, pretty easy, yeah? So inspections, measurement. So we were inspecting if this thing is conforming. We're inspecting if this part is conforming to our standard right there. So toolmaker's part within the standard deviation of the designer, okay, part. So standard deviation, this can be plus or minus, okay, 5% of that part. So what is the 5%? You're gonna multiply 0.05 with this, okay? So that would be your 5% tolerance or standard deviation, meaning like you can deviate, okay, deviate from 40 in the positive direction or in the negative direction. Positive, bigger, negative, smaller than this thing, yeah? All right, come back. Okay, so we're in the industrial technology, so there are two basic types of measurement. We don't do the third one, only two. So anyways, linear is measurement of translation, and angular is measurement of motion or rotation. Linear and then angular. Linear translation, angular motion or rotation. So let's take a look at this picture. So all measurement, they require three elements. One is the part you're measuring. You're using an instrument to measure the part, and you have a standard to compare your measurement to. If you measure this and compare to the standard, if you come really close, your measurement is accurate. You measure this one time, 2 times, 3 times, 4 times, 5 times, 6 times. And then you look at your 6 data. If they come close to each other, data close to each other, okay, we call that precision pretty high, yeah? We have a two method. One is interchange and the other one is displacement. Interchange, if you look at it in a diagram, you have a standard and you have the part. First you measure your standard, you measure the part, and then you compare, okay? So that's, we call that comparison. Doesn't really matter, you can start with the part and then you can measure. What we're trying to do is measure this measurement and then that measurement and then you compare. And we call that both ends observed at the same time, yeah? Now, displacement method is a direct method. The ends are observed separately. So here, when you look at the picture, you're going to see here is a measuring device, and there is a part, and here is a standard. You're going to measure the ends, okay, separately. This B is pretty difficult for you to be able to see it right now, but you will get it. Okay, so right now try to get the terms a little bit interchange, displacement, get that interchange with comparison. Okay, get that displacement is a direct measure. Okay, so the chapter 1 accuracy and precision is repeated right here in chapter 2 with some diagrams. Okay, so you can visualize it. But then you already know accuracy comparing to a standard, precision, you're just looking at your own data, okay? Or a repeated measurement of your part, okay? You have different sets of data measuring the same part, and then you look at how precise your measurements are. So anyways, when you look at this guy, you're gonna see, okay, measurement is definitely influenced by variables. So when you look at it, okay, for shooting, you're gonna be able to see this guy shooting a target, okay? He wanted to be at the center of that, but then you will have different kinds of variations, okay? Then you have 1, 2, 3, and then 4, and then 5. So if you make this one bigger and bigger, you can see all of this, okay? Just trying to tell you, like, you have variation in the shooter, okay? Then you have variation in the rifle, you have variation in the environment, okay? And then you also have a target, okay, with a different results. So these are all variations. So if you get like they can be different, because if they're not different, you'll be shooting at the same position on the target, right? But every time you shoot the target, you have different points coming on that target, so therefore there is variation, and that variation is depending on who is firing what rifle and how the rifle is being held in the hand, okay? And at the time that person is doing this action, because the environment is different from every second to another. So a second before and a second now and a second after, they're different. Okay, there might be wind or there might not be. There might be rain or snow or something, because everything is different. There might be somebody talking to you or not. So the environment, when you think about environment, don't think about just mountain and trees and things like that. We're not talking about that kind of environment. We're talking about everything, okay, in the space around you, okay, around the system that you're considering. So anyway, let's go into the 210. So here you can see a big picture in your textbook or the handout. So you can see A, B, C, D, and E. All right. Then these are my score. Don't worry about it. So when you go here, you see, look at this. Okay, shots right there, shots right here, shots right here, here, and here. When you look at this, okay, that's pretty accurate because you're comparing that to a standard. Okay, where is your standard? Your standard is the target itself, this one, all right? The target set, you're pretty good if your shots are within this 1, 2, 3, 4 diameters right there. So now when you look at it, here out, this one inside of that standard target map, okay? See, everything is inside. So that's mean pretty accurate because you are comparing your data, okay, to right here. And that's your standard. It said if your shots are within this target, okay, alright, within this target, first diameter, second diameter, third diameter, the full diameter, then you're pretty accurate. So therefore accuracy is pretty accurate here, see. D is precise, so when you look at it, look at that. Your own data, 10 points, okay, 10 points out of the standard here, on the standard, okay, but we don't care about the standard anyway, but you're within, your consideration. This is outside of the consideration. And look at that. Every time, whoever is shooting right here, look, that person is getting right at that area. Bang, 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 bang. Not anywhere here, okay? They're not evenly distributed right there. Every time you shoot it right here. So therefore, precision is pretty high in this case. This one is out of the map, right? So therefore, even if every time this person is shooting, okay, but accuracy is pretty off, yeah? Precision high, but accuracy is pretty off because it's off of the standard map, yeah? Precision is not good because they're all spread out. Precision, pretty good. Accuracy, low right here. Accuracy, pretty high. Precision, very low. And here, accurate and also precision, precise. So therefore we call that reliable. Yeah, you have both of them. So that you've got this and you've got that. So therefore you are reliable. Accuracy. This is precision. This is reliability. Okay. Your stuff are accurate. Your stuff are precise. Your stuff are reliable here. This is not very good. Accuracy is completely low right here. Here, precision is low and accuracy is kind of okay, yeah, but not as good as that. I think you can be able to see it by now. And you don't have to read the whole thing, just try to study that and you should be able to get it, yeah. Alright, the next one is a 211. Now we're going to change the variable, and that is it's windy, okay. When it's windy, you have to hold, okay, your rifle right here, a different manner so that you can be able to stand, okay, your wind which is subjected to you and the rifle, okay, because there's a disturbance in the environment, so you have to adjust the way that maybe you have to put more energy to stabilize your rifle, okay. Shoot again. So now you can take a look at it right here. Still accurate, okay. Precision kind of low because the accuracy is pretty kind of becoming off. Okay, this is pretty off. This one, accuracy is low, also precision is kind of low. Here, precise, and then accurate, still almost standard compared to the standard. The data points compared to the data itself is kind of precise, only hitting that area. Yeah. Again, accuracy, this is precision, there's reliability, data are accurate, data are precise, and here the data is reliable. A little bit off compared to the first, right? Because now we have a factor, and the factor is wind is messing up. Alright, the next diagram is a change in the second variable. We're gonna reduce this target size, okay? Make it a smaller target. So let's see. And you shoot again. So when we make the smaller target, there is also a wind right there. Yeah? Look at that, same thing. Kind of accurate, kind of precise, and kind of. This is still reliable, yeah? So we can see the range is pretty small right now. Range again, small right now. So now you understand the variation, different factors, they can change. Everything changes in the world. Nothing is the same from second to second, by the way. You know accuracy, you know precision, and you know reliability, okay? And you gotta get that. Alright, so let's move on. Here is a formal way of presenting precision, accuracy, and reliability with terms, okay? Meaning, general meaning, measure that, and method of stating, and specific meaning. You can read that by yourself, okay? But what I really want you to get is the nature of them, okay? When you write it down, you can write it down with your own words. That's fine. Alright. I want you to read through 2 to 7 and then 2 to 8 by yourself. And this is kind of like a scavenger hunt right there for the quiz questions are. Okay, and as you read, you can find the answer and answer that. So they're not very important, okay, for our course, but you should know. So just read through. This is just your reading assignment 2, 7, and 2, 8. Okay, so to determine the best system, we look at the easiness and then the usefulness. The usefulness is based on your methodological, computational, and communicative factors. Your easiness is based on this 4, okay, potential, time, error, and the cost. It's got to be cheap, you should be able to use this system in a very short time, and the error got to be pretty low, okay, potential got to be great, yeah. So those are the things that we consider for easiness. Those are the things that we consider for usefulness, and if you can come up with that, you'll get the best system. Alright, this is the factor that we are looking at, or everything this, and we judge the metric and the inch pound this way. Okay, these are based on historic data. That can be changed depending on the group of people who are using that system. Okay, some people are leaning on this, some people are leaning on that. However, we have only two major systems that we use. Most of the science industry and domestic. So I'm going to erase this. Again, the key point is usefulness and easiness, okay, to determine the best system. Okay, so now when you take a look at this, we see this is your decimal inch system right here. System is nothing but a big word. Just trying to tell you like what kind of measurement system, okay, that we're using to get the measurement. And we use a unit, decimal inch here. And we call them the decimal inch scale, right? These are the divisions. So if you want to measure a linear measurement, you're going to measure one point to another, and you're going to get that measurement. And you'll be using these divisions and the scale, right, to describe your measurement. So precision of fractional inch scale is so important. If your instrument isn't precise, it will be very difficult, right, to use it. Simplicity of the metric system, it got to be simple. If it isn't simple, nobody want to use it. So that when you take a look at the metric rule, okay, you're going to see how simple that is to come up with a linear measurement. When you look at this thing, look at that fractional inch. So this one, we use it only for the precision study here. Usually in the lab, this is commonly seen instrument that we use outside. You can see kids are using that in elementary school, middle school, high school, and you are using it in university as well. Okay, this one is a decimal inch. Okay, so when you look at this 1, 2, 3, we usually use this. Okay, why? Because it's pretty easy, simple to use. Yeah, so most of the people choose the easiest instrument for them to be able to do the measurement. This is only for like research. Okay, if you want a precision, then we use those kind of scale. So anyway, you kind of get the idea. So I'm gonna erase that. Go to the next one. Okay, so next one is a decimal system. We already know what decimal system is, yeah. So here 1, 2, and 3. That's for the comparison in computation. So we have fractional, we have exact decimal, and we have two-place decimal, right? System and equivalence for that system. So why do we use a decimal system? Is because it's pretty good for computation, okay? So we have computational advantage by using decimal system. So therefore we use it. So here we can do addition like that way and subtraction like this. So if you go with a fraction, it's pretty difficult, right? You have to write like 1 by 64, 9 by 32, and then 31 by 32. So just by doing a data entry in fractional form is causing you a lot of time. So therefore we do decimal. Yeah, decimal, you can just write 1.015625, bang, finished. We can simplify that by using only two place. Two place means 2 decimal points, so 1.02, round it off. See like how compact this is a lot of fraction, and we change it into decimal exact. And then we're gonna round it off, so 2 place. Yeah. So when you look at this, look at that, how clean the data is by looking at this thing. Yeah. You don't want to deal with this for computation. You want to deal with something simple. So science is nothing but making everything that's complicated so long and short to the point, easy, simple form of writing. Okay, and you still get, all right, pretty good estimate. This is exact and that's estimate. So 1.015625, that's about 1.02, yeah? But it saves a lot of time and headache, yeah? So anyway, this is for subtraction. So the point is, we make it easy, okay? Short to the point, take little time to do something. So therefore we use decimal system with round, okay, rounding off. This is just a successive housing and just a review from your SAT. So 1, 1/2, 1/4, 1/8, 1/16, 32, and the 64th. If you look at the decimal, it's like that. We usually go 2 digits, yeah. If you go into the left, we go around 4 digits, yeah. This is nobody really do that except for the precision calculation or computation or serious computation for building robots, spaceships, or things like that. Okay, airplane, then we use a pretty precise one. All other things it cuts off around here, yeah. Okay. Now you have a job to review, rounding off. You should know how to round. If you forget about how to round the number or the value, okay, you should review this. So that's your high school review, yeah. So we do the round off using the general rule right there from 1 to 3. So why do we have to round off? Because we are eliminating the unnecessary figures in any computation. Science is to make it simple. In order for us to make things simple, why do we make things simple is because we want to cut time. Okay, we want to do so many things in a short time. So you got to eliminate all the junks. Okay, so if you have unnecessary figures, that's you don't want to carry that in your computation because it's taking so much time and stress, give you stress. So therefore, you're going to simplify by eliminating all the unnecessary stuff. Okay, here in this case is your figures. So that's why we have to round off the stuff. So how do we round it or follow that rule? We have rule 1, rule 2, and then rule 3. So you can review that. Okay, I want you to get this. Put some time to do this. There are a couple of questions in the quiz. You know the quiz that you just download that, and as you read and study, finish that quiz at the same time. Okay, all right. Okay, so we're going to continue the rounding off numerical value from your last slide. Okay, so when you take a look at this, and we have 2 rules, one is round up and then the other one is round down. So all you have to do is just to review that too, okay? Just read through, and I'm not going to go over that again. You should be able to know rounding out is if you look at the decimal 4 here and look at the number, okay, after the full decimal, and you can see right here 0, yeah. So 0 is less than 5, so therefore you didn't do anything. We go to the third decimal here, which is 5. You look at the number after that, which is 5, okay. So therefore you're gonna increase one number up here. So you got 2.076, okay. Rounding down is even though you have 5, you're not going to increase 1, okay. So therefore you get only 2.075. Yeah, and that's the difference. So anyway, you do everything in that table, round up and round down. This is just showing you the calculated volume. You don't have to know this. If you go over that and take a look at it, you will see some numbers. This is just showing you the total of this number data set right there for round up, and this is for round down. Okay, a set of data. They're not related here. They're different example. Here you can add it up and you will get this. Okay, and you're just comparing this with that. Yeah, this with that. And the difference is over by 0.02. This is under by 0.01 because you're rounding down, rounding up, so over by 0.02. Okay. Because this is 0.132. This is only 0.15. 0.132. This is 0.1.12. Okay. We ignore 7001 because they are the same. So the difference is between this 132.15 and 132.12. About that much. And that is the average from here all the way to here. Okay, so the same thing we ignore because they're the same right there, 1400. So we pay attention to here. 226 is your true, all right, value. This one 23, so therefore higher than 226. 224 is lower than the true value. See that? So we call that round up, and this is round down. Is another way of getting tolerance zone, yeah, your standard deviation. So these are all estimate. We're estimating up, estimating down how far away you're far away this difference from the true. You're far away the difference from the true value, which is more accurate. This guy, yeah. Why? Because the difference is smaller than that. Yeah, so when you look at the table and the data, just by looking at it, you should be able to come up with all of that. Okay, so if you cannot get it up the first time, make sure you look very carefully and then slowly each one of them. Okay, and there's a way to read the number. So reading the number, in the fastest way is eliminating everything that is same. So if I'm reading this number, I am eliminating that because I already know that's the same. Yeah. So when you look at it, you're looking for the difference. So what is the difference? You should be able to know that just by looking at it. Here is the difference. What is the amount of difference? This one. How did you get it? Subtract it. Yeah. See how it's so easy to read it if you target what you're looking at. If you're reading the whole thing and just confusing, clutter your mind, right? So get rid of everything that is the same, because these are called the redundancy. Okay, so that's how you mine the data set. So you should be able to read even a long line of data. You should be able to read the difference like that. So here, that's your positive standard deviation, and that's your negative standard deviation. Yeah. It can go up to there, it can go down up to here, but then you're around that true value. Yeah, high is on this side and low is on that side. And this is the exact true value right there. But what we do, okay, we have that difference, a little bit of difference, but then this difference is going to save you a lot of time. Yeah, by estimating it instead of going exact. So therefore we trade the time by doing estimation. How do we estimate? We estimate it up or we estimate it down. It usually comes around, right? The true value. All right, so I'm going to erase this. All right, here we go. So a lot of the SAT questions are that, if you remember your high school. So if you think about SAT, sometimes some of the questions won't give you the exact calculation. You're spending so much time using your calculator and trying to find the answer. No, there isn't. Okay, you have to estimate and find the answer that's closest and best to the situation presented in your MCQ. So that's how you do your SAT and ACT. Any kind of standardized tests are like that. Okay. Okay, so that's it for today. Yeah, for chapter 2. Make sure you do your quiz.